Hello, welcome to the course Electronic System Design. Last lecture we were discussing about some general concepts about PCB. How do we design a PCB right from the footprint creation to the final routing. And then we discussed if we have a normal PCB, the design rules are very relaxed. However, if we have a high speed PCB where the frequency of operation inside the PCB or at the input output, if the signal is transitioning at very fast rate, then we need to take special care in designing those PCBs which are called high speed PCBs. So now today we are going to discuss some concept, something called signal integrity, that when we have a high speed circuit or a high speed link from input to output or inside a circuit, how much is the ability of our circuit to transfer this data from one place to other place without any distortion or degradation. That is something called signal integrity of a PCB. So let's discuss these concepts now for high speed PCB design. So we have a very important concepts of signal integrity. So this signal integrity or SI signifies the signal's ability to propagate without any distortion. Signifies the signal's ability to propagate without distortion. These signal integrity issues must be taken care of during the PCB design phase only. Once the PCB is fabricated, there is very little work we can do to improve this signal integrity. So we need to do it right in the PCB design phase. So SI issues must be taken care during the PCB design phase. Once fabricated, very little can be done to improve on this, or it's very difficult to improve on SI. So we have signal integrity, which signifies the signal's ability to pass or propagate without much distortion. There will be some amount of distortion definitely, but it should be within the acceptable range. And these SI issues, these are very important issues. Without this, if we fail on the SI issues, the chip or the complete circuit will not work. And all these issues must be taken care in the design phase only. For example, if we are designing a chip at the chip design level, or if we are designing a PCB, then at the PCB level itself all these issues need to be addressed, because once the PCB is fabricated, all those traces these are fabricated, then it's very difficult to improve on SI, because we cannot change the length, width or any other parameter on the PCB. So once it is fabricated, it's very difficult to improve on the SI issues. So all these issues should be taken care of within PCB design only. So what are these issues now for high speed design? So as we know, when we have a signal, even if it is a digital signal, but when it is passing on a trace, all these signals are fundamentally analog in nature. So even if we are supplying it, for example, square pulse, which has a very high rise and fall time, but this is not a discontinuous signal, it's a continuous signal, which is a analog signal fundamentally. And all these signals, they are susceptible to noise. If there is a noise somewhere in the environment, that noise has its certain voltage, and we are sending a data which is also in the voltage form, 0 volt or 5 volt. So this voltage will be coupled to that noise voltage, and that signal will be switching based on whatever is the noise voltage received from the noise source. So now my signal is mixed with noise, and it will lose its sharp edges, or the signal will degrade. Let's see how this look like in real time. So first of all signals are fundamentally analog in nature. So in this graph, let's say this is the signal which we apply or which we want to transmit. So this is the transmitted signal, or sometime we call it the near end signal. We send this signal, and now this signal, we can see this is kind of perfect pulse signal which we are sending. However, in between, when this signal is traveling on the trace, this trace has some coupling to the new noise source, and this is the noise, this is the voltage of noise, this is with time. So this voltage or noise voltage is coupled to the trace where the signal is traveling. So this signal will be subject to this noise, and the output or the resultant at the far end will look something like this. So this is very degraded signal. Ideally it should be like a pulse signal, but because of the noise, this has so much of noise overlapped on the signal. So this looks still a bit okay, but here we have very much degradation in the signal. So this is the received signal or the far end signal. So this is one possible cause of degradation where the noise is coupled to the signal. The other can be the rise and fall times, which are very fast. So let's discuss some signal integrity issues. So this high rise and fall time or the faster rise and fall times are the most important cause of signal integrity issues. Is a faster rise fall times. So how these fast rise fall times actually create signal integrity issue? For that we can draw a sample track. For example, we have a track which is made up of copper, and this has relatively longer length. So this length is high for this copper track, and at the other end or the far end this is terminated by certain load resistance or the receive or the far end. At the near end we are applying a signal to this. Now when we apply this signal, for example, we are going from low signal to high or the high to low signal. Let's say initially we have a high signal which is, let's say, 5 volt here, and initially the signal was in stable condition. Throughout this length of trace we had this 5 volt, and suddenly we pulled this signal from 5 volt to ground. So initially let's say this was the 5 volt voltage, and suddenly we pull it down. We pull it down here. So we assume that the length of this trace is relatively large, so immediately the signal will not reach from near end to the far end. It's going to take time because this trace now acts like a transmission line. So at the input we have pulled from 5 volt to 0. It means this at the input, this has gone down from 5 volt to 0 volt. However, at the far end this is still at 5 volt, and this 0 volt is being transmitted from input to the output at, let's say, at certain amount of time. After, let's say, a small amount of time delta t, the signal has reached, or this 0 level has reached from near end to, let's say, this distance. So here we can see, as we pulled down the node at input, this input or this 0 volt is going to take some time in reaching from input to output, and this change is gradually going from the near end to the far end. Now this is our rise time. Now this rise time is small compared to time of flight. Time of flight is the total time the signal takes from the input to the output. So now rise time is much smaller than the time of flight. So this is the signal integrity issue which comes because of high rise time and fall time, or the faster rise and fall time, means the shorter or the smaller rise fall times. We can actually divide these various signal integrity issues into multiple categories. So the first one which causes the signal integrity issue is the impedance discontinuities. These are the very common factors which affect the signal integrity in a PCB. This is impedance discontinuities. The second issue is, or the second cause which creates signal integrity, is the reflections, ringing, overshoot and undershoot. overshoot and undershoot. Then crosstalk, via stub, skew and jitter, and the sixth one is signal and attenuation, ground bounce, power and ground network, and EMI noise. So here we discussed when we have a signal which is having a very high rise or fall time compared to the total time of flight which the signal takes from input to output, that time this creates problem in signal integrity, and some of the issues we can characterize in some categories for signal integrity. The first one is the impedance discontinuation, where we have mismatch in the impedance. Reflections, when we are sending a signal it bounce back at the far end, so that is reflection. Crosstalk, we have neighboring another trace which is also carrying certain signal which can be coupled to the main signal. So we have all these issues which we can categorize in different categories. Let's discuss one by one each of them in little detail. The first one is impedance discontinuity. So what is the impedance discontinuity? We have a trace which is carrying a signal. If there is no bending or there is no change in the geometry of the wire, then signal will flow just normally. But if there is a mismatch or there is a change in the size of trace, that will act as a boundary for a signal, and the signal will be bounce back from that discontinuity. So that creates a impedance mismatch in the trace. When we have a straight trace, for example this is a 50 ohm characteristic impedance, and suddenly we have a thicker trace which is joined to this thick, the boundary between this thin trace and this thick trace, this boundary acts like a mismatch of impedance. So that impedance will not be now 50 ohm characteristic impedance, but it will be different than 50 ohm, which is a problem in high speed PCB design. So let's see how that comes in. So the first one is impedance discontinuity. So if a signal encounters a discontinuity in impedance during its travel, it will suffer reflections at the far end. This will happen when a signal encounters a via in its path, which is very common case in the PCB design. Many a time this trace ends up at a via, which is a impedance discontinuity. So a signal encounters a via in its path. For example, in this diagram, let's say we are sending the signal from X and we are receiving this signal at point X dash, this orange color pad, we are receiving this signal. Now this signal starting from X into this trace has some characteristic impedance, let's say 50 ohm. This characteristic impedance is a function of the track width. Let's say this width is 1 mm, and based on that we have characteristic impedance of 50 ohm. So when this signal is passing from X and reaching this point, now this is a via, which is, for example, we have two layers. In one layer we have this brown color trace, in the other layer we have this orange color trace. These are connected through this via. So these vias, because this width is not 1 mm now, this act as a impedance discontinuity. So this is very common case in PCB design. For high speed designs we need to take care of these things. The second is when a signal branches out into two or more lines. So in this case, for example, we have this trace, we are sending the signal into this from point X. After certain distance, this is branching into two. So this trace splits into two traces. One goes to X dash, one goes to X double dash. So here we see The characteristic impedance is function of this thickness. At this point, this thickness is not exactly the same. For example, this is 1 mm, then this is a different shape than a straight trace. So this interface act like a impedance discontinuity for the signal, and the signal will bounce back at this discontinuity. So this is called branching out into two or more lines. The third very usual case is the signal return path encounters a discontinuity like a split. In this case, we have some return path for the signal, and if there is a discontinuity or a split in that return path, that also causes impedance discontinuity. The fourth one is line stubs, which can be connected to signal lines and are quarter wavelength. So line stubs are connected and are 1 by 4 lambda of switching speed. In this case, let's say we have a trace which is carrying some signal, and at some point we have an extra piece of this trace connected. So this is x, this is x dash, and let's say this goes to some other point. This may or may not be terminated. So this extra length which is connected to this main signal is called stub, and if this stub is the length of this stub L, let's say this is L from this point to this point, if the length is 1 by 4 lambda, then this stub act like a quarter wave transformer, which will significantly impact the speed or the signal which is propagating from x to x dash. Signal and return paths are connected to connector pins. So when these traces, when they start or terminate at some pins, these pins are generally piece of metals at the terminating end or at the starting end. So this acts like a impedance discontinuity. So here we have x, this is x dash, and the signal is going from x to the connector pin. This acts as a discontinuity in the impedance. So all these factors, wherever we encounter this kind of case, we try to omit or we try to have the impact of these factors smaller in the PCB design if we are having a high speed PCB design. So this is the issue caused by impedance discontinuity. Next we discuss the issue because of the reflection, ringing, overshoot and undershoot. So what is a reflection? So when we have a signal which is passing through a trace, the impedance of this trace, which is constant with this width, so throughout the length the width is constant of this trace, and suddenly at some point we connect a different structure. It may be circular, it may be a via, it may be another trace joining this trace. So anywhere where this width is changing compared to this current width, that interface acts like a impedance mismatch, and wherever there is a impedance mismatch, this signal which is flowing into the trace will see that impedance mismatch as a boundary, and the signal will bounce back from that boundary into the reverse direction. So we are sending the signal, let's say in this direction. At that interface or discontinuity, signal will hit and some of the portion of signal will come back into the sending end or the near end. Some portion will be reflected. So that is called reflection in the signal. This happens because of impedance mismatch, and because of this reflection there can be a ringing. Ringing is something, we have a voltage, it should be stable at, let's say, 5 volt, but because of these reflected waves, this reflected wave again will go at the near end. There also there is a discontinuity, it will bounce back, some portion of it will come forward and then again bounce back into reverse, it will go backward. So this forward and backward movement, because of this there will be a reflection or the kind of ringing will happen inside the voltage. So this 5 volt which we are assuming it's a constant 5 volt, this will have certain amount of ripple type of variation on this 5 volt. So this is called ringing, and sometime when this reflection is very high, this creates the overshoot and undershoot in the waveform. So let's say we are applying a 0 to 5 volt signal, but because of this reflection, this 5 volt can also go sometime to 6 volt, which is the highest voltage in the circuit. We are not having any 6 volt source in the PCB. All the voltage we are using is 0 or 5 volt, but because of the reflection, some amount of voltage will be superimposed on this 5 volt. This 5 volt will become 6 volt. This is called overshoot, and this is very dangerous for the circuit reliability, because all of our circuit, when we design, we assume that 5 volt is the maximum voltage which will happen, and all the circuit is safe up to 5 volt only. If there is a overshoot which is very high, for example it goes to 6 volt or even 7 volt, then our other circuits which are seeing this voltage, or this voltage goes to some gate of a MOSFET, that MOSFET is only tolerant to 5 volt. If this 6 volt goes into that MOSFET gate will be damaged. So our circuit may have damage because of this overshoot and undershoot, and these happens because of the impedance mismatch only. Some portion of the signal is bouncing back, get superimposed on the main signal, and the main signal will rise above its desired highest level. So this is called reflections, ringing and overshoot and undershoot. So let's discuss this in detail. So whenever the impedance changes in a circuit, some amount of reflection will happen. When a signal is transmitted in a transmission line, some of the signal power may be reflected back. To its transmitter. Rather than being carried all the way along the trace to the far end. So when we have a signal which is transmitted into a transmission line, some of the signal, so here it is some of the signal, not all the signal, some part of the signal, maybe 10% or 20%, This much of the signal power will be reflected back to its transmitter. If we are sending from the left, so this will bounce back from the right and will again go to the left, rather than being carried all the way along the trace of the far end. So not all the power will reach the far end, 10 or 20% will come back to the near end. The reflected signal will travel back until it encounters another change in impedance and get reflected again. So this is, let's say, point 1. When it is reflected back and going back to the near end, at near end again it will see the discontinuity and some of the portion will bounce back again from near end to far end. So the reflected signal will travel back until it encounters another change in impedance and gets reflected again. The influence of reflection is a signal distortion and overshoot undershoot. And how to reduce this? First is we maintain the constant impedance. We maintain good ground plane and we have proper termination. So here we have a signal which is going from left to the right. At right, which is far end, we have impedance discontinuity. So some portion of this signal will pass through and some portion, 10 to 20% or 30% depending upon the impedance mismatch, 20% let's say goes back to the near end. Now at the near end again there is a impedance discontinuity, and some portion of this 20%, let's say again 20%, so 20% of 20%, this 4% of the power will again bounce back at the near end and goes again to the far end. So this process will continue. So there is a bouncing at near end and far end. This produces the ringing in the system, and the influence of this thing is signal distortion. The signal get distorted and overshoot and undershoot happens in the signal. How to reduce this kind of effect? The first is to maintain constant impedance. Though it looks simple to say that we need to maintain the impedance constant, this is very difficult, because anywhere you are terminating this trace, you are connecting anything to this trace which is going to change its size, that is a impedance mismatch for a signal. So anything you connect, this is going to disturb your impedance. So it's very difficult to maintain a constant impedance. The other thing is good grounding. So these ground planes need to be run along the trace, that we need to take care by proper grounding and proper termination. So at the far end, the trace need to be terminated with a constant resistance, let's say 50 ohm. So this 50 ohm need to be a proper 50 ohm, it should not be changing with voltage or time. So the proper termination is needed to suppress the effect of these reflections. So let's see in graphical view how a reflected wave or this ringing happens and how does it look like in a system. So let's define what is ringing. So for example, we have a signal which is shown here by red color. This signal is the signal which we are sending into a media, and because there are signals which are bounced back at near end and far end, because of that certain voltage is actually superimposed on our signal, and the actual signal after superimposition look like this yellow signal. This yellow signal, if we look like, we have this signal going up, down, going up, down from its desired value, which is this red line. So this signal is actually going up, down multiple times. This is called the ringing in our signal. So ringing is a voltage or current output that oscillates like a ripple So this forward or upward downward movement, this is called the ringing. Next is the overshoot. And undershoot. So let's say we send a signal which is a pulse wave, and the desired output is shown by this blue curve. So the ideal output what we want is this blue pulse. However, because of the reflected wave which is getting added to this level, this VDD, now this level is something VDD, the actual desired level, plus V noise or the reflected voltage, V reflect. So because of this addition of this reflected wave into the VDD, now the output actually goes above the desired value, which is this VDD. This is called overshoot. And the same thing happens here when this 0 volt or the ground volt is mixed with V reflected, and V reflected is such a way that this is subtracted from 0 volt. So in that case this signal goes below 0 level. This is called undershoot. Here also there is one undershoot here, then overshoot here, undershoot here. So this overshoot and undershoots are the when the signal transits from lower value to higher value and the value of the transit signal is more than the actual value, then overshoot occurs. So when the value of transit signal is more than the actual value, that is called overshoot. Similarly, undershoot, when the value of transit signal from higher value, when the signal transits from higher value to lower value, and value of transit signal is less than actual, then we say there is a undershoot. So here we discussed two important concepts. One is the impedance mismatch. If there is an impedance mismatch, then there will be a reflection of signal at that boundary that will cause reflection or ringing or overshoot and undershoot. Ringing is when this reflected wave is coupled with the incoming signal. The signal will have ripple type of variation at the input at the high level and low level. So that is called ringing. Overshoot is when this voltage is coupled to the high level and creates a peak, that is called overshoot, and when it goes down, that is called the undershoot. And these overshoot and undershoots are very dangerous or very problematic for our circuit design, because this high voltage or this extra voltage creates a high voltage stress on our other circuits. This may get damaged because of this high voltage. So, these overshoot, undershoot, ringing and reflections, these are not desirable, and we solve these problems using impedance matching. We try to make a constant impedance in the PCB design. So, these are the 2 points we discussed. Rest we will discuss in the next lecture. That's all for today. Thank you.